Hello, good morning everybody. So, we are discussing rate processes. So, under this heading we started to discuss theories of reaction rate. Okay. So, theories of reaction rate. So, last day we talked about this transition state theory. Before that we talked about collision theory. So, now it is time to have a comparison of means whether we can make any comparison between these two theories. Now, before that let us try to recap about recap these two theories, means basic like basic postulates of something. Say what is collision theory? So, collision theory is based on a hard sphere model that one molecule or an atom is there and reacting. Okay. Reacting means this reaction occurs via this collision, occurs via collision. Okay. So, and this collision is purely based on the idea that these spheres are hard spheres, that is molecule or atoms, okay, those which are involved in collision process. Okay. So, they are hard spheres. So, it is a hard sphere collision theory. Okay. And this collision theory is based on the concept of means it was borrowed from the concept of kinetic theory of gases, that like in kinetic theory these gas molecules. So, this basically this collision theory is applied to gas phase reactions. Okay. So, in kinetic theory it is postulated that these molecules are in a random to and fro motion within a container, and there is a collision between molecules or atoms. Okay. And maybe this there is collision with the wall as well, wall of the container as well. Now, it is thought that this chemical reaction occurs as a result of this collision, as a result of this collision. So, if there is no collision, then there is no chance of reaction to take place. So, so if this is a redistribution of atom, or maybe if there is an exchange of atom between two interacting species is there through reaction. So, in that case these two species or these two parts should come in close contact at least once, so that they will have a chance to exchange. That is why collision is required. Okay. And it is also explained in this way that not all the collisions are very effective. Only those collisions which are having, means the molecules those which are having some requisite amount of energy, at least some minimum amount of energy, okay, will be able to react further to produce your desired product. But if the energy is less than a definite amount, then the reaction will not take place. Even if there is a collision, those collisions are not effective. Okay. And also properly oriented collision will lead to product formation. But in all these cases it is important to note that we do not have any idea of exactly what is going on when two molecules are colliding with each other. When these two molecules are colliding with each other, what is happening here in this region, in this region where there is a contact. So, we do not know, we have no idea on that, what is exactly going on. Only the gross idea is that we have got two hard spheres, they are just doing this collision and then reaction is taking place. So, it is just a kind of qualitative idea, it does not give lot of insight. Okay. Now, in transition state theory, what is there in transition state theory? Transition state theory says that an activated complex will be formed during the course of reaction. Okay. So, one molecule, there is one molecule, there is another molecule, they will form an activated complex, maybe something like that, an activated complex. And this activated complex will have higher energy compared to your reactant molecule or product molecule. Okay. And this higher energy state is called the activated state. So, once activated state is reached, then the system, I mean system means this activated state, has got the option to move forward to give you products, or maybe it can come back, to give you the reactants back. Okay. So, the thing is that in activated complex theory there is a definitive option of structure, okay, that maybe if A and B, or maybe two interacting species which are undergoing a chemical reaction, they will form, say, an additional linkage between them, like say like this, say you have got A, you have got B, and we can imagine that from this, okay, it will form something like a weak interaction. Okay. So, this is your activated complex. Okay. Then this activated complex will react further. It may go back to give you reactants as well. Okay. So, there is a definitive option for the geometry or internal structure of this. Okay. And the thing is that there is a quick equilibrium established between A plus B with AB activated. Okay. So, this is a fast equilibrium, and then this activated complex is gradually depleted to give you your products. Okay. So, of course, we can tell that your collision theory is not that much definitive, but this activated complex theory, or maybe your transition state theory, it tries to talk about a structure, an internal structure of this species. And also importantly, it talks about a mode, means out of the many modes, say this is a multi-atomic species, it will have 3 translation, then if it is a nonlinear, then it will have 3 rotational, and remaining will be your vibrational modes. And out of these vibrational modes, a specific vibrational mode will have high amplitude and a low frequency. So, that high amplitude low frequency vibrational mode, okay. So, that will be ultimately converted to a translational mode. Okay. So, you have to take out one of the many vibrational modes of the molecule or the complex and convert this to a translation, and this translation is responsible for passage, okay, from one side to another. So, this particular vibrational mode is responsible for passage from left hand side to right hand side out of the many vibrational mode, and that is a weak vibration, okay. And that happens with your this activated complex, okay. So, a definitive structure and also which particular mode could be responsible for this formation of the product, we can also deduce that, means with the help of your this theory. So, definitely collision theory, it appears that collision theory is much more weaker than your transition state theory, although collision theory can successfully explain your rate constant observed for many gas phase reactions, and also it can explain the temperature dependence. As I told you that if you think of Maxwell distribution of molecular velocities, and if you increase the temperature, then you will be seeing that the plot, that is probability versus c, that is the velocity or the speed of the molecule, if you increase the temperature, the graph flattens and your most probable velocity is shifted to the higher region. And if you think of a definitive amount of energy, the number of molecules having that amount of energy or more than that will be increased as a result of increase of temperature. So, that means you will have more number of successful collisions, and therefore, more reaction will take place. So, temperature dependence can be well explained with this theory, but it is rather qualitative. It cannot explain exactly the structure of your of the species which is responsible for the reaction to take place. That is, it does not think about any species of this sort. Okay. And what is exactly going on during collision is not also very obvious here. Okay. So, it can successfully explain the temperature dependence, but it is weaker compared to your transition state theory. Okay. And if you think of transition state theory, your entropy of activation has got connection with your steric factor of the reaction. Okay. And similar term is involved with collision theory, which is called also the probability factor. That is, not all the collisions are effective, only a certain fraction of these collisions are responsible for reaction to occur, that is with proper geometry. Therefore, collision theory, if we compare these two, so collision theory, transition state theory is on the upper side compared to your collision theory. Okay. Now, let us have some idea of the degrees of freedom. Now, the thing is that given that the total number of degrees of freedom for a polyatomic molecule is 3n, that is, polyatomic molecule means you have n number of atoms. So, polyatomic molecule. So, how many degrees of freedom for this molecule will be there? There will be total 3n degrees of freedom. For say for a monoatomic case, say only one atom, how many degrees of freedom it will have? It will have 3 translation in 3 mutually orthogonal axes. Now, if we increase number of atoms by 2, that means if it is a diatomic system, then what will happen? You have a diatomic molecule. Okay. So, how many translational degrees of freedom will be there? Still it will be 3 translational degrees of freedom, okay, because it can move in 3 mutually orthogonal directions. Okay. So, that is its center of mass can move in 3 mutually orthogonal direction like this. Okay. Now, what about rotation? It will have, so it will have, since this has 2 atoms, so it will have 3 into 2 altogether 6 degrees of freedom, of which 3 will be translation. So, minus 3. So, that means you have got rotation plus vibration to be equal to 3, of which let us try to find out how many rotational mode and how many vibrational modes are there. So, if you think of, say, this is a diatomic molecule, okay. So, if you think of rotation about its axis, it does not give you a new configuration, okay, new way of representation. Okay. So, that means rotation about the internuclear axis is trivial. So, it does not contribute to the overall degrees of freedom. Now, if you think of rotation about this axis, it gives you new configuration like this, another is this. So, rotation about this axis will contribute to your rotational degree of freedom. So, this is one rotational degree of freedom about this axis, and there is another like this about this axis. Okay. So, total 2. So, therefore, 2 rotational degrees of freedom, remaining how much? 1, which will be vibrational. Vibration means like this vibration. Okay. So, that means it is for a diatomic system you will have 3 translation, 2 rotation, 1 vibration. Okay. Now, the question is calculate the number of vibrational modes open to A, an atom, B, for a diatomic molecule as I explained to you, C, for a nonlinear polyatomic molecule with n atoms, and there is a nonlinear activated complex with n atoms. Okay. So, how to look into that? As I told you, for an atom it will have no vibrational degrees of freedom, just translation, just simple translation like this way or that way or maybe the other way. Okay. So, it will not have any rotation or any vibration, because it is a spherically symmetric. The atomic system is thought to be spherically symmetric. Okay. Now, for a diatomic molecule you will have, as I told you, you will have one vibrational degree of freedom, that is only it will have this motion, this vibrational motion, that is it will lengthen and it will shrink, this motion. Okay. And for a nonlinear molecule, okay, so for a nonlinear molecule, say this is a nonlinear molecule like this. Okay. So, it will have 3 translation, as it is obvious that this will have a center of mass may be located somewhere over here. So, it will move this way or maybe that way or maybe this way. Okay. Now, what about rotation? Means if you think of rotation about this axis, say for example, then this rotation will lead to something else. So, it will not lead to any indistinguishable configuration. So, maybe it will have a rotation like this axis, maybe that axis, and maybe another orthogonal axis. So, since this is a nonlinear system, you will have 3 rotational degrees of freedom. Okay. You will have 3 rotational degrees of freedom. Okay. So, therefore, you have 3n minus 3 and minus 3. So, that means 3n minus 6. Okay. So, 6 will be counted for 3 translation, 3 rotation. So, remaining will be 3n minus 6. Okay. So, 3n minus 6 will be the vibrational degrees of freedom, or such number of vibrational modes are there. Okay. What about nonlinear activated complex? What about the nonlinear activated complex, that since it is a nonlinear activated complex, like it is a complex, maybe you think that it is some aggregate kind of thing. So, it will move like this, maybe this way or maybe that way. Okay. So, it will have 3 translation. In the same way, like your nonlinear molecule, it will have 3 rotation as well. Now, the question is what about your vibrational mode? Can you guess what will be the number of vibrational modes? So, you in that case, in order to find out that, you have to take help of transition state theory. Okay. It says that for the reaction to take place, because your nonlinear activated complex will for sure undergo reaction to give you products, or maybe it will come back to give you reactants. So, to give you products, what you have to have in order to get your product, out of many vibrational degrees of freedom, one will be taken out, and that will be converted to translation, and your rate of barrier passage will be equal to kT by h, that is the kT is the thermal energy divided by the Planck's constant. Okay. So, that is the frequency with which it will pass the barrier. Okay. It will pass the barrier is the rate with which it is reacting. Okay. So, that means out of many vibrational degrees of freedom, one will be taken off, and you add that to your total translation. That is, initially it had 3 translation plus 1, you call that it is internal free translation or internal translational mode. That internal translational mode is responsible for the reaction to occur, internal free translation. So, therefore, you have altogether 3n minus 7, okay, minus is somehow dropped. So, 3n minus 7 vibrations are there for a nonlinear activated complex. Okay. So, if you apply transition state theory to find out, find out the number of degrees of freedom, that is vibrational degrees of freedom remaining for an activated complex, then you have to think of that out of the many vibrational modes. Out of the many vibrational modes, one will be taken off. Okay, one will be taken off, and that should be added to the translation, and the one which is added to translation should not be called as a direct translational mode, but it can be called as an internal free translation. Okay. Next, so transition state theory, and now this is the rate constant for your transition state theory. It is kT by h, e to the power minus delta g double dagger 0 by RT, which has got your exponential this entropic term, and this is your enthalpic term. Okay. So, it is a simple bulk phase reaction, but what happens if the reaction occurs on surface? Do you think that the expressions are different? So, let us try to look into that. Okay. So, transition state theory applied to surfaces. Okay. Now, when there is a surface reaction, okay, when there is a surface reaction means surface means it is a region, again region of inhomogeneity. If you think of a glass of water over here, okay, you can have 2 regions. One is inside the glass, which is called your bulk phase, and the top of layer, water layer, you have got your interface. Okay, you have got your interface. So, like this. So, you have got a glass of water, okay, and water is up to here. So, this is your bulk, and this is your water vapor interface, okay, liquid vapor interface, and this is called the region of inhomogeneity. Here it is homogeneous, in this region it is homogeneous. So, if you think of the composition, then composition everywhere same. Okay. But here you see, the moment you cross this boundary, you will be seeing density is reduced a lot, and also number density of water molecules will also change, that is, will also reduce enormously. Okay. So, this is called the region of inhomogeneity. Okay. And lot many things may happen over here. Suppose you put some surfactant molecule, that is like detergent. then what will happen, these detergent molecules having like tail and a hydrophobic group. Okay. So, this tail, hydrophobic tail with a polar group, plus or minus, or maybe uncharged with some polar character. So, what will happen, this charged one or the polar one will be directed this way and the tail will be like this. So, adsorption of this, this molecule, the surfactant molecules will be there. Okay. So, when there is a question of region of inhomogeneity or surface, then appropriate substances may get adsorbed onto the surface, so that the bulk concentration may be different from your surface concentration for the same substance. So, when you think of a surface reaction, so that surface reaction must have a component that your reactant will adsorb onto the surface on which the reaction is taking place. They may be on the metal surface. So, in the adsorption of atoms and molecules, we need to distinguish between two cases. Two cases may happen. Okay. One is called the direct adsorption, another is called the indirect adsorption. The direct adsorption process is one in which the particle collides with the surface. Surface means your maybe the metal surface, and stays at the point of impact as an adsorbed species. So, that means the moment the molecule or the atom hits the surface, it gets a position. It gets a position means it gets one chair, a vacant chair, where it will have its sit. So, it will be seated over there. Okay. And it will stays at the point, that is at the point of impact. But in the indirect mode, what is happening, that the particle first adsorbs in a weakly bound precursor state. That is, initially it will just maybe get adhered to the surface of the metal, but there is no strong linkage. Okay. It is a weakly bound situation. So, it is a weakly bound precursor state in which what is happening, that it will have the option, it will have the freedom to move around over the surface. Okay. It will have the freedom to move around over the surface until it gets some permanent position. Permanent means like although nothing is permanent, like it will have a better set where which is basically vacant for this incoming particle. Okay, that is, it will get some vacant space where it will make a make a bond. So, that means the moment, so for your indirect adsorption, it comes onto the surface, then it moves around, it looks for some position, some seat, okay, where it will, means if it gets a seat, then it will definitely form a bond. But initially when it has hit the surface, there is a weak linkage. Weak linkage means it hits the surface, but it remains adhered to the surface. It will not go out, it will just move around the surface until it can find out a space for its sit. Okay. So, for indirect adsorption process, the transition state is that of a two-dimensional motion over the surface. So, it is very interesting. If we think of an indirect adsorption process, then as I told you that the first process, what is happening is that there is a weak linkage formation. Weak linkage means weakly bound to the metal surface, and the moment it is weakly bound, it just moves around your surface. Okay. So, it is a kind of two-dimensional motion. So, this dimension is taken off, although in gas phase reaction it has got the option. If you think of collision theory again, then it is colliding. So, it is moving to and fro in all possible directions like in 3 dimension, but here the moment it is weakly bound to the metal surface or to the surface, then it does not any longer go this way perpendicular to the metal surface, it is not doing that. So, only it is moving this way in 2 dimensions. So, that is indirect adsorption, the transition state is that of a 2 dimensional motion over the surface. So, it is a kind of transition state. Okay. So, it didn't have any specific position. So, that is why it is moving around. So, the transition state is with a 2 dimensional motion. Okay. After some time, this mobile precursor state, why it is a mobile? Because it is moving around. Okay. So, mobile precursor state, after some time this atom finds a position, a site, okay, which is free for its occupancy, and a possible chemical linkage may be formed at the surface. Okay. So, this is the situation with indirect adsorption process. Now, the other option, the direct adsorption process, the ground state of the atom, since before the atom gets adsorbed onto the surface, the atom is in the ground state. Okay. So, the ground state of the atom is in the 3 dimensional space over the surface. That means, here it is thought that you have got the metal surface, and on top of that metal surface there is a little slice, okay, 3 dimensional space in which this these atoms are moving around. Okay. So, it is thought that the ground state of the atom is in the 3 dimensional space over the surface of the metal, and the transition state is fully immobilized atom on the surface side, which is not allowed to move around, and the transition state is a fixed state. It does not have the option to move here and there. Okay. Unlike your indirect adsorption, which is a case of for which your transition state is in a 2 dimensional motion over the metal surface, but here no, it is not the case. It does not have the option to move in a 2 dimensional space. Only thing is that there is a slice volume space over your metal surface. Okay. So, the atoms are initially there, and then eventually it will stick onto the metal surface. Okay. So, this way the other option, that is the direct adsorption process, occurs. Okay. So, that means when there is a question of surface reaction, then the question of adsorption comes into picture, and the adsorption means it may be a weakly bound situation, like it may be a physisorption, or maybe it is a weakly bound situation, or maybe a strongly bound situation, which is thought to be the case for your direct adsorption process. So, let us go for indirect adsorption process. So, think of an atom which adsorbs onto a 2D mobile state. Mobile state means it is moving around. So, that is why it is a 2D mobile state. Okay. It is in 2 dimension. No, this dimension is not allowed, only this dimension or maybe that way it is allowed, okay, over the metal surface. So, so it binds here on the metal surface, a weakly bound precursor, that is transition state, and then it is moving around like this, and then eventually it gets a position. Okay. So, atom adsorbs onto a 2D mobile state, and suppose we have got Ng number of gaseous atoms. Okay. So, Ng number of gaseous atoms and m number of sites on the surface. So, you have got the site, m number of such sites, and Ng number of gaseous atoms. Okay. The mechanism is that the atom this is the surface, the star is the surface making a mobile situation. Okay. So, it is a mobile precursor, that is this precursor is moving around. Okay. And per unit area, this is the number of sites available per unit area. This is m is the total number of sites on the surface and A is the area. So, if you divide by area, then it will be giving you number of sites per unit area. So, this mobile then gets converted to mobile, but it is the right one, that is your A star state. Okay. So, after it has got some position, okay, maybe one vacant position where your A atom is adhering to. Okay. And also the idea is that we have to apply here since it is a case of equilibrium. So, chemical potential of the atoms in gas phase and in the double dagger state, that is your activated state, these two are identical, thought to be identical. Okay. So, rate of formation or rate of formation of this A star, which is nothing but the frequency with which it is formed and your n number of atoms in the dagger state. Okay, this n star. Okay. And where K double dagger is your the equilibrium constant is your n double dagger divided by n g. So, it is g to double dagger kind of thing. Okay. So, therefore, d n A star dt is equal to nu K double dagger n g, and also the fractional coverage due to A star is your n A star divided by total number of m sites, that is sites available for adsorption. So, this is your theta A star. Okay. So, suppose you have got like say 100 over here, say 100 means m is equal to say 100, and suppose that n double dagger is 50, that is maybe 50% is occupied, then what will be theta? Occupied means after the daggered state is getting converted to some confirmed position, that is not like a mobile, it is moving here and there looking for some position to occupy. Okay. So, it is a confirmed state. So, theta A star is equal to n A star divided by m. Okay. Therefore, you can write d theta A star. So, time rate of theta A, that is your after it has from the precursor activated precursor to a adsorbed state to the adsorbed state. So, that is equal to d n A star dt divided by m. Okay. So, that is equal to nu K double dagger n g divided by m, which is equal to nu K double dagger by m. Now, you have to write in terms of P A, gas pressure of A, P A, then V is equal to N G, then N G K B T. Okay. So, you can write in this way. So, if you substitute this is your number density. Okay. It is your number of, it is not the mole, it is the number density N G. So, you can write for this, you can write V kb T into Pa, which is equal to transition state theory K TST Pa. Okay. So, that means we started with this indirect adsorption mechanism, adsorption of atom, and the idea is that your mechanism, as I explained here, that A with the surface producing a weakly bound A, okay, mobile phase, and then this mobile phase is converted to your adsorbed phase, and once this adsorbed phase is produced, then this adsorbed phase undergo some reaction. So, that is why your rate of change of Na star with time is written in this way, where theta is the coverage, fractional coverage, and from this we arrived at this relation d theta A star dt is equal to k T S T into Pa. Next is, what is K double dagger? K double dagger is, since it is this activated state and your gaseous atoms are in equilibrium. Okay. First they will form an equilibrium, like if you think of this step, you see this is an equilibrium. Okay. Therefore, you apply mu g is equal to mu double dagger, and if you apply your statistical mechanical expressions from partition function, then mu is equal to minus kbt del ln q del n, okay, and q gas is equal to total q gas is equal to individual particle gas particle to the power n g divided by n g factorial, and in the same way total q double dagger is equal to q double dagger to the power n double dagger divided by n double dagger factorial. Okay. And for this qg is equal to q translation, because it is a gas phase case. So, this gas molecules, since these are not adsorbed, these gas molecules are not adsorbed. So, it will have, these gas molecules will have the option to move around in 3-dimensional space. So, this will be basically it will have translation, okay, only translation degrees of freedom. So, qt to the power in 3D, okay, and for double dagger it will be your q trans in 2D times a q v, that is we have taken out one vibrational mode out of this many modes. Okay. So, that means why 2D? Because now as soon as the gas is confined, gaseous atoms are confined, they will have the option to move in 2 dimension only, this way or maybe that way, in 2 dimension only. So, this third dimension that is moving to this way, that is to the top this way, okay, this movement is not there. Therefore, we have taken out this vibrational one out of this translational modes, one is taken as your vibration. Okay. So, therefore, K double dagger is equal to n double dagger divided by n g is equal to q v double dagger q translation 2D divided by q translation 3D. Okay. So, 1 degree of freedom is taken out as a product. Okay. So, what you can write, d theta star dt is equal to dNA star by m dt, okay, which is equal to nu k double dagger Ng divided by m is equal to nu into k double dagger by m into V Pa by Kb T, which is equivalent to K TST P or Pa. So, K TST is equal to nu. So, K TST you have to just this part accepting Pa, this part. So, K TST is equal to nu K double dagger V by Kbt and divided by m is equal to V, now QV double dagger, then Q translation 2D divided by Q m into Q translation 3D, okay, into V by Kb2. Okay. Then if you put the respective expression, because it is a 2D, it is a 3D, and simply if you simplify that, this dimension means if you have this plate or the surface like say A, this is A, then your 2 dimension will be area will be A square, third dimension will be A cube, like that. So, if you put this, you can, if you put the respective expression for your translational mode, okay, if you put this expression for your translational mode, then you can write for your translation it will be 2 pi m m kbt to the power 3 by 2, since it is 2D, therefore 2 by 2, 2 by 2 means 1 by h square. So, for this part we wrote like this, and here it will be 2 pi m kb t to the power 3 by 2 divided by h cube, of course V by kbt, kbt. Okay. What will happen to this one now? Now, and of course, you have to write, and here one term will be there A, and here it will be V. Okay, V means volume, it will be area, okay, because it is 2 dimension. Okay. Now, what will you write for this one, this nu? Okay. So, you can write for this one to be equal to for this case you can write express this one, means this remaining part you can write your kb kt by h, basically kbt by h, because this represents your the partition function for your vibrational thing. Okay. So, what you end up at is your, this is equal to, since V is there, this V gets cancelled, this A is remaining, and this H square with H will give you H cube. So, this H cube gets cancelled. So, ultimately what you get is A divided by m. Okay. Okay, let me write it in a separate page. So, ultimately KTST will be equal to A area divided by m. Okay. M is the total number of sites into square root of 2 pi m kb t. Okay. So, this is equal to 1 by n 0 per unit area, m by a is n 0 into square root of 2 pi m kb into T. Okay. So, that means d theta a star dt will be equal to P a into k T s t, that means P a by n 0 square root of 2 pi m k b into T. Okay. So, this is your fractional coverage, rate of fractional coverage change. Okay. So, from this we can write n 0 d dt of theta a star is equal to m by a d dt of theta a star, which is equal to 1 by a d n a star dt, which is equal to your P a by square root of 2 pi m k b T, which is nothing but your rate for the collisional mechanism, collision theory that you are getting from collision theory. So, R collision. Okay. So, if you think of this indirect adsorption mechanism, then you get similar to a rate expression similar to what you get for the collision based on collision theory of surface reaction. Okay. So, this corresponds to collision on a surface, okay, since the atoms are still free to move in 2 dimension. Okay. So, it is basically this corresponds to, as I told you, that surface collision. Okay. So, ultimately we ended up to a very simplified expression that your d dt of theta a star has got your P a divided by n 0 into square root of twice by m k b t. Okay. So, it is this corresponds to the collision on a surface, since the atom are still free to move in 2 dimension. Okay. Because it is similar to what you get in other theories, that they are moving around, they are moving around on the surface, although the 3rd dimension is off, this dimension is off, but they are moving around. So, there is option for them to collide on the surface. Okay. So, today I guess I should stop, and in the next lecture we will talk about direct adsorption mechanism. Okay. Now, so what have we learned out here, that in this particular lecture we started to discuss this transition state theory applied to surface reactions, and there are 2 modes of reaction. One is your indirect adsorption, another is your direct adsorption. So, today we talked about this indirect adsorption, and ultimately we came to a conclusion that even if it is even if the your reactant is bound to the surface, although maybe it is by a weak force, but they have the option to move around onto the surface, and maybe they will make collision. Okay. So, it gives you a similar to collision rate. Okay. And we also discussed this with taking some example about this your degrees of freedom, especially a nonlinear activated complex, how many vibrational degrees of freedom are there. It is actually 1 less than a corresponding molecule, that is same number of atom containing molecule or the molecule containing the same number of atoms as your activated complex. Okay. So, in the next lecture we will talk about your direct adsorption mechanism, and we will try to find out the expression of rate out there. Okay. So, till then have nice time, we will see you in the next lecture. Thank you.